Good afternoon, class. Today we're going to continue working with proportions, but we're going to work with them in using similar figures. So we're going to build some objects and then find some missing side lengths. So first, let's just talk about what it means to have objects that are similar. In a situation like this, when we're working with similar figures, we're looking at similar figures here if they are alike, but not necessarily identical. So they don't have to have the same size, but they will look like they're the same. So in this situation up here on the right, similar figures, we have similar glasses. So they're the same shape, but they're different sizes. In mathematics, similar figures have the same shape, but are not necessarily the same size, just like these are. There's a symbol we're going to use, this little tilde symbol here. Is for similar figures. And in the problem down below, we're going to be talking about triangle ABC, which is this smaller triangle, is similar to triangle DEF. So DEF. So in the similar figures, the measures of the angles are all going to be the same. So angle A here, angle A, would be the same measure as angle D down here because they are what we consider corresponding angles. So corresponding just means that they are located in the same location. So angle A and angle D would be considered corresponding angles. Just like angle C, here's angle C, and angle F would be corresponding. And then angle E here and angle B here will be similar or corresponding. Side lengths are not equal. So in this situation, we have AB and DE are corresponding. So AB, down here along the bottom, is corresponding to DE because they're in the same location, even though this triangle is flipped. So we would just write that in a fraction. Anytime you're dealing with similar figures, we can use fractions. So AB is a side length. We can write that in a fraction with DE. And then we can work with the other corresponding sides just the same. So AC, which will be the long side here, is corresponding to DF along the other side. So that can be put in a triangle or in a fraction as well. And then the last side, BC, is this upright one, and FE or EF is the other corresponding. So we'd write BC over EF. So the neat thing about similar triangles is that these fractions, once we get them all set up, are all equal. So we can use our knowledge from our previous lesson that proportions, that's what this is, we have a proportion. Proportions are equal to each other, so we can solve for missing side lengths using this. So that's what we're going to do in the first example here. So here's an example. We have a triangle ABC is similar to triangle DEF. So we can see that AB and DE are similar sides. They're in the same location on two different triangles. BC and EF are similar. They're the same location on two different triangles. And then the bottom, AC and DF. So what we can do is we can use this knowledge that these are going to be equal to solve for the missing side lengths. So we can start with trying to figure out if we know AB is 10, but we're trying to find DE, we can use this proportion and the one that we know both side lengths on, BC and EF, so that would be this middle one, and just substitute the side lengths in for the sides. So 16 is BC's length and 12 is EF's length. So then over here, if we're trying to find DE, we can put 10 in for AB and just let X or some variable represent the missing length over here. So if this was the missing length, we're saying we're trying to find that X. So now we're just going to cross multiply. So we're going to do 10 times 12, which is 120, and 16 times x, which is 16x. So we're just doing our cross product here, just multiplying those. Now we just need to take 120 and divide by 16. So we'll divide by 16, and we'll get x equals 7.5. So we can find the other missing side the same way. AC here can be found in the same manner. So we can take the 16 over 12 that we knew BC and EF were equal to, and just set that equal to AC. Let's call this y here, trying to find y. So y over 18. We're going to do the same type of thing. We're going to cross multiply. So we're going to get 12y equals 16 times 18, which is going to be 288. Divide by 12 to get y equals 24. So we know y equals 24. So we can find missing side lengths. The next example is going to be referring to objects in nature and how we can set up a proportion using shadows. The sun will cast a shadow that is proportional as long as the two items are relatively close to each other. We couldn't talk about the shadow of this person down here and the flagpole if they were miles apart, because the shadows would not be similar because they're not in the same location. We have to be referring to shadows that are of two objects that are similarly close to each other. So we're going to take a person which is 6 feet tall. So we know that this is 6. And then the flagpole, which we don't know. So we're just going to let that be x. We don't know the flag height. I'm going to put my 6 here. X, we don't know that. But we do know that the man's height and shadow to be 3.5 is the shadow, and the flagpole is 17.5. So think of this as like two triangles. This triangle and this triangle are similar triangles. So we could set up a proportion and try to solve for this x. So we would do that by just putting x over 6. The flagpole and the person's height would be in the same fraction. And then 17.5 over 3.5. So you have to be careful here when you're going to set up your second proportion. The two top numbers have to come from the same item. So x and 17.5 both correspond to these, the flagpole and shadow of the flagpole. And the other proportion belong to the man's height and shadow. So, excuse me, the height and flagpoles of the man and the flagpole are the same here. So you have to be careful when you set up these proportions. There are other ways to do this. So we could have set it up as these two in the same proportion, but then these two would have to be in the same proportion. I think I misspoke earlier. So we're going to cross multiply here. We're going to take 6 times 17.5 to get 105. And then we're going to take 3.5 times x to get 3.5x. Divide by 3.5 to get our answer. And we can get that the flagpole is at 30 feet. So we know the flagpole sits at 30 feet. These are all approximate heights based on the shadows. We can also use proportions when we're looking at maps and scaled drawings. Blueprints is another example, and you'll do one in class using blueprints. So for the example here, we're going to be talking about a scale map where 1 inch is 110 miles. So typically you'll see a little scale on a map, and what that map is telling you is that any measurement on the map is referring to a total distance in real life. So in this case, every 1 inch that you measure is actually 110 miles. And what we're going to be doing is the distance from Jacksonville to Gainesville on the map. So here is Gainesville, here is Jacksonville, and what they're saying is this distance right here, sorry, I'm a squiggly line there, is 0.6 inches. So we're going to use this idea of a scale, and we're going to set up a proportion. So 1 inch and 110 miles, we can set that up in the 0.6 inches that we know and what we're trying to find in miles. So we would just cross multiply here, and we would take 0.6 and multiply by 110, and we would end up with 66. And obviously 1x when we cross multiply. So in this case, the distance x is going to be 66 miles based on our scale. So we can use scale drawings and use proportions as well. You're just going to set it up as if it was a triangle, some similar triangle, and set up a proportion for those. So we'll do some more examples in class. Answer the questions after the video and bring any questions you have to class.